part 2 of hidden surface removal. Okay, so we saw. Okay, guys. Okay, got your attention now. Okay, so we saw in the this morning that one technique, which is called back-face culling, just removes any polygon which is facing away from us. So if that polygon is facing away from us, we ignore it from now on. And so this is what we're left with. So this is my virtual world, and I've removed any back-facing polygons. The good news is my objects now look solid. Solid meaning opaque, not solid meaning good. Okay, stream slang. But the bad news is we have this building here, like this churchy type building. This should be behind this this house here, but it's not. Okay, so whilst back-face culling does make objects look solid, it's not the full solution. Okay, which brings me on to our next method, and this is called the painter's algorithm. Painter's algorithm is quite easy to remember because it's named after what you do is when you paint with oils. Now, do we have any artists here? Artists. Okay. When you paint with oils, unlike watercolors, oils are opaque. So when if you were painting a landscape with oils, you'd have to paint the background first. Okay, so this is like the 3 stages of showing an example of painting with oils. So you paint a landscape, the background first, then you paint the middle ground, and then you fill in the details at the front. So those are the steps when you paint with oils. And it's essentially what we do with the painter's algorithm. Okay. What we do is after back-face culling, you should have a set of all front-facing polygons. And what we do is you sort the polygons into descending order by the smallest z-space coordinate. So what we mean by the smallest z-space coordinate is polygons are represented by a number of vertices. And those vertices may have different, or they will have different z-coordinates. Now we just want one value for the distance, so we take the closest vertex to the viewer. Okay, so you sort the polygons in descending order of smallest z-coordinate, and for all your polygons on P, going in the order they're sorted, you plot the current polygon. So you're starting with the furthest polygon away, you plot that, then the next furthest, and the last polygon you plot should be the one which is closest to the viewer, hence obscuring anything behind it. Okay, so here's an example. That's again my viewer at position P, and here I've got 3 polygons. So 3 walls, and let's assume that they're all front facing. Okay. And I've got what we call projectors here. Now, if at the end, after I've completed this, anything which is to the underneath of this projector here, okay, apart for this polygon should be obscured by the polygon which is in front of it. Likewise, anything which is underneath of this projector, we can see polygon B, but anything between there and there, we shouldn't see the polygon B. Okay, so if I attempt to represent this, so this is polygon A, so that's a polygon in the background. Okay, if I then overlay polygon B, and then finally I overlay polygon C. So that's what you see after you've done all polygons, and you can see most of polygon A is actually hidden. And this happens when we do this in, I say in real life, when we do this with a real virtual world, most polygons aren't seen on screen because there's something in front of them. We still have to take them into account because they still may be in the viewing frustum, they still may be within that unit cube, but after you do hidden surfaces, they may be obscure, but they still have to be taken into account. Does have a problem. What are you going to do in this case? Okay, here we've got 3 overlapping polygons. And by this I mean each polygon is like both in front and behind another polygon. So which do you do first and which do you do last? So this particular case, our painter's algorithm wouldn't be able to work. So what we then do is, if we have a case like this, we cut up a polygon. So for example, if I take this one, I can cut this into 2, I can cut this into that polygon, and a second one there, and treat them separately. And that cutting up of polygons is what we're going to be seeing in the last method, which we'll talk about today. Okay, so painter's algorithm, it's a very, very simple algorithm. All you do is start with the furthest polygon and end with the closest, but it's not the complete solution because it doesn't work for this case. Okay. In my example, as you can see, I've taken the backface culling virtual world and I applied painter's algorithm, and then it did work. I haven't got it to show you here, but when you do that helicopter thing and you do the painter's algorithm, it does sort of it works in most cases, but sometimes it does sort of buildings do pop in front of each other. So it's not the total solution, but it's part of that. Okay, so that's the painter's algorithm. Everyone okay with that? If something's in front of something else, it's obscuring it. Is essentially the principles behind that. Now this brings me on to what's known as a Z buffer. Now Z buffer applies a similar concept to the painter's algorithm, but on what we call a pixel by pixel basis. So when you're looking at a computer screen, you're not looking at an image, you're looking at thousands and millions of tiny little dots, and those dots are called pixels. And what the Z buffer does is, for each pixel on your screen, it works out the painter's algorithm. Okay, so what we do is we create 2 arrays. So we have an array, which these 2 arrays are both the same size as the pixels on your screen. So if you have 640 by 480 pixels, you'd have 2 640 by 480 arrays. That's quite low resolution. I think now you have 4, for example, you have 4K televisions, which means 4,000 pixels wide by however many pixels high. Okay, so for each pixel on your screen, you have a space in that matrix, in that array. Now the 2 arrays, one's called the depth buffer, or often this is one which is colloquially known as a Z buffer. And what it does is, for each element in the array, it stores the depth of the nearest surface in the aligned world space for that pixel. So if you can imagine, when you have a polygon, we'll go back a slide or 2. So let's say we have the roof of this building. If I was to fill that in, all the pixels which represent that roof, okay, will have a different distance, okay, because it's sloping away. Okay, if I was to look on it on top, these would have a different distance. Okay, so for each pixel on that roof, okay, this is the closest surface for that pixel. Okay, so the depth buffer, each pixel on your screen, it records how far away are we to the nearest surface. The frame buffer, this stores the index of a polygon. By that index, I mean what's the color of that polygon. So for example, if we had a red polygon, which was in front of a blue polygon, the frame buffer would record color. Did I say red in front of blue? Yeah. Red in front of blue, the frame buffer would record the fact that that's a red pixel. Okay, so the Z buffer method is the same principle as the painter's algorithm. The fact anything in front of it obscures anything behind, but it does it on for each pixel. Let's here's the actual algorithm. Not yeah. Let's step through it. So you've got a set of polygons, and we create a depth buffer array Z and a frame buffer array F. And we start with all of our elements in Z is set to Z max. That's your maximum draw distance. Could be the same as the maximum viewing plane. For all polygons in your set, and for all pixels in the current polygons, what you do is you think, okay, what pixels represent that polygon, and you loop through all those pixels. We calculate the Z coordinate of the point corresponding to the current pixel. If that Z coordinate is less than that of the number already stored for that pixel, we replace the number already stored with our Z coordinate, and we replace the corresponding frame buffer element with the color of that current polygon. And you do this for each polygon. Sometimes you'll have a Z coordinate that will be less than the one already stored. Sometimes you won't. So at the end of it, whatever's stored in our Z buffer is the closest distance for each pixel. And then whatever's stored in the frame buffer, the F array, would be the color of the pixel, which you then show on screen. Let's have a look at a worked example. Okay, here's an example. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have a 10 by 10 screen, 10 pixels by 10 pixels. I start with, now I've used infinity, but this is just some large number. Okay. So my frame buffer is filled with lots of large numbers. My Z buffer is filled with lots of large numbers. My frame buffer is just empty. Notice they're both the same size. Okay, what I've got here is I've got a polygon, and in the frame buffer, each of these numbers represents the distance of the polygon from the viewer. Okay, so you can see on the left-hand side, the left edge of the polygon is close, but this sort of point of the polygon is far away. So it's kind of like facing sort of like that, away from you guys. Okay, and that's a red polygon. So what I did is I looped through all of these pixels, and because the distance, the Z distance, was less than infinity, I've replaced those distances there. And in the frame buffer, the corresponding pixels I've drawn in red. Okay, so that's one polygon. What if I have to add another polygon? Okay, so that was my one polygon. Now I've added another. Now on this polygon, it's a square-shaped polygon. The left edge is closer, but then it's going further away here. So we're going to have times when, if we look at this pixel here, okay, that had a distance 5. Okay, so that value for that pixel there had a Z value of 5. When I look at the next polygon, that distance was 4 for that pixel. Because it's 4 is less than 5, I then replace it, and I also replace, change that from being a red to a blue. Okay, so these are two sort of polygons which is kind of like sort of overlapping each other, and you can see the Z buffer records the distance, the smallest distance for each pixel. You do that for all your polygons, and you're guaranteed to get good hidden surface removal. Okay. Right, so how do we calculate these pixel coordinates? Okay, we have, remember after clipping, we have a screen space which goes from -1 to +1. Okay, and we're going to assume that we have a number of pixels in the horizontal direction. So nx is number of pixels across. Aspect ratio is the width to height. Okay. Our pixel coordinates have to be whole numbers, can't be 0. Okay. It has to be between 1 and an x. So we're going to have to scale our screen space coordinates so that they're pixel coordinates. Okay. If nx is the number of pixels in the horizontal direction and aspect ratio is the width to height, then we simply calculate ny. Now, remember, nx and ny have to be whole numbers. Screen space coordinates are in the range -1 to 1. Pixels on the display are in the range 1 to nx. Okay, so we're starting to deal with discrete values. Okay, so if we want to scale, we find the pixel coordinates using this. So you calculate your scale. Okay, so in this case, we divide nx and ny by 2. So x scale times our screen space coordinate plus 1. What that does, screen space coordinate plus 1, okay, add 1 to both of those, you get a range between 0 and 2. Divide it by 2, you get a range between 0 and 1. Multiply by the x scale, and that scales your coordinate. So if you had, let's say you had 10 pixels, okay, you'd multiply your screen space coordinates plus 1 by 5. What we have here, though, is a max of 1 or that number you've just calculated. The reason for that is this could sometimes give you a number of less than 1. It could sometimes give you 0.4 or something like that. We can't have that. We need ours to be in the range 1 to 1x. So that's where the max is. Okay, going to be doing a bit of what's the word? Interpolation now. Okay, because we're dealing with pixels by pixels of a given polygon, what we need to be able to do is calculate the position of each pixel within that polygon. Now, this is something we'll be looking at in a couple of weeks, but for now, we're going to do it in a more simple method. What we do is you loop through horizontal rows of pixels. These are called scan lines. Okay, so we take each row of pixels going from the top to the bottom of the screen. And for example, here's a row. Now, for each row, you calculate where the edge of the polygon intersects with your row. So that dashed line is our scan line. That point A is when that left edge of the polygon intersects with the scan line. That point B is when the right edge also intersects with the scan line. You do that by interpolation, linear interpolation. These are known as scan extrema, A and B. C, position of C, is then calculated by interpolating between A and B. So that's how we calculate the interior pixel coordinates. Remember, we have to do this for x, y, and z, because we need that z value for the z buffer. Okay, what about the mathematics? Well, you got to remember, we're starting at the top and going down in whole numbers. We're going down in pixel by pixel each time. So that means if you have two scan lines, so this scan line we know, the value of the y coordinate for this scan line is simply the value of the y coordinate for the upper scan line minus 1. We're going down 1 pixel. It's the x coordinate which we're going to have to calculate. So in this case, on the left-hand side, we have an x coordinate which is there, and then it goes to the left a bit to give me this x coordinate. And the distance it goes is called delta xa. And likewise, on the right-hand side, if you've got this coordinate at one scan line, if we go to the scan line beneath it, we're going to the right a bit, and therefore, so we've got delta xb. Okay, delta xa and delta xb are calculated using the coordinates of the vertices. Okay, so YA is easy to calculate. That's whatever your scan line is. Minus Y0, which is the Y coordinate there, divided by Y2, which is that Y coordinate, minus Y0. And similar for the right-hand side. This is not something I'm going to ask you to do. It's not something I'm going to ask you to apply, but this is just generally how we do it. Okay. And then we go across. So once you've got the end points on your scan line, you interpolate across. So you start at the point A, we go left to right, and we move across. The x-coordinate for the next one is simply whatever your x-coordinate on the one on the left, plus 1. Because remember, we're going pixels. That have to be plus 1. Y-coordinate is simply whatever the y-coordinate of A is, because it's got a horizontal line. So that's easy. Calculating x and y for those pixels is easy. What is trickier is calculating z-coordinate. Remember, this is screen space. It's a 3D. Okay, even though we're only plotting x and y, we've still got that depth information. So we need the z-coordinate of all pixels within that polygon. And what we do is we use our old friend, the vector equation of a plane. So remember, n is a normal vector. R is any point on that plane. So any point here, okay, it doesn't matter which point we choose, it'll give us the same. And S is some number. Now, if you know what the z-coordinate is, and remember this is distance into the sort of background, if you know what the z-coordinate at that point is, if we go one to the right, all we have to do is subtract nx over nz. Okay, if I show you how that's actually done. Yeah, I've missed out a bit. Just to show you how that's done. So we start with n dot r equals s. Okay, vector equation of a plane. What I'm going to do is actually expand this out. So that's my normal vector, nx, ny, nz are each component. And I'm going to say that's my point R. Okay. And that's going to be some number S. Actually, I might have included it in your notes. Oh, I have. Right. I might as well carry on doing it. Okay, well, I've already said our point X and Y is easy to find. It's this point Z, or the value of Z, which we're trying to find. So if I expand out this dot product, but nx times x, ny times y, plus nz times z equals to s. Okay. I'm trying to find z. So that's easily rearranged with s minus nx times x minus ny times y over nz. Okay, so that's the equation linking my z-coordinate with the normal vector. I know what the x-coordinate is, I'll know what the y-coordinate is, and I'll also know what s is. What I'm going to say is this is for my ith pixel. So remember, if I've got something like this, here's my scan line. That's my pixel Ci. This is my pixel Ci plus 1. I know what x, y, and z is at that pixel. What I'm trying to find is x, y, and z at that pixel. X is easy because it's just whatever that is plus 1. Y is easy because it's on a horizontal line, so it's just whatever that y is. Z could be anything. So what I can say is the z-coordinate for the next pixel over is minus nx times xi plus 1. I'm going 1 across. So instead of xi, I'm going 1 across, so I'll get xi plus 1. Minus ny times yi, all over nz. Notice that nx, ny, and nz are constant for all points on that plane, and so is s. Expand out the bracket. So if I expand out this bracket, minus nx minus ny yi all over nz. And I can split up into 2 fractions like that. Okay, so just to recap, this is the coordinates of my ith pixel. So the one I already know, I know all those values. The one at the pixel, the next step to the right, I have to add 1 to my xi value. So I'm just going 1 pixel to the right, expand it out, and I can break up that fraction into those 2. Now, if you have a look at that right-hand side, that fraction and that one, they're the same. So what I can then do is say, well, that's just going to be equal to the zi coordinate, which I already know, minus nx over nz. So it's a very neat sort of result. If I know the z distance for the pixel to the left, the pixel to the right is simply that distance minus whatever nx over nz is. Very, very neat, easy thing. So it's not actually that difficult calculating the z pixel coordinate. And furthermore, nx over nz is constant for that polygon and can be pre-calculated. Okay, so the z buffer, computationally quite cheap. Okay, we're having to do all that interpolation when we'll see when we get onto filling methods later on this term. We're having to do that anyway, so we've got all that information. It's efficient, but it uses a lot of memory. So if I take a fairly, I'd say reasonable, this is quite low res for modern displays, but 1280 by 1024. So that's the 1,024 rows of pixels and 1,280 columns, which is a fairly standard, well, a couple of years ago, it's fairly standard display. If you had 16 gigabyte, what we call RGB color, okay, this means RGB color means red, green, blue. You mix red, green, blue together to give all your visible colors. And a 16-bit RGB color, and a 24-bit depth buffer. So that's how accurate you can get your depth buffer to be. Okay, so let's have a look at how much memory it uses. We need depth buffer plus frame buffer. Okay, so you multiply each pixel, so you've got that many pixels, 1,280 by 24, plus it's multiplied by the depth buffer memory for each pixel, and do the same for the frame buffer for each pixel. Do these sums, and you get 52,428,800 bits. And there are 8 bits in a byte. Okay, so that works out at 6.5 million bytes. So roughly 6.5 megabytes. That's for each frame. So each frame you actually use in 6.5 megabytes just to store the information. But good news is memory is cheap. Okay, you know by your phones and your computer you can have gigabytes of memory in, and you can buy sort of pen drives quite cheaply with lots of memory. Memory is cheap compared to the cost of the processor. So it's better to be computationally efficient, but use more memory than it is to use less memory, but be more computationally efficient. Right. Okay, and there is on the activities, there is a one for the Z buffer. I'm going to carry on to talk about binary space partitioning because it's more relevant to your assignment. We may, if we've got time, we may come back to do that activity. Right. So that's Painter's algorithm and the Z buffer. Okay. They both work on the premise that something in front of something else obscures it. It means you can't see through it. Now, this is also the premise behind binary space partitioning. But what binary space partitioning does, it sets up the information for the Painter's algorithm. It sounds quite sort of grand, binary space partitioning, but we often shorten it to BSP. Okay, and this, what this does, it produces a data structure in what we call a BSP tree of the polynomials in the world space. Okay, so after we've done the BSP, you'll have what we call a tree, and that's what we're going to be looking at now. Okay, it determines which polygons needs to be split or not. So I mentioned Painter's algorithm doesn't always work. Sometimes you have to cut up polygons. BSP will do that. And BSP can be done, it can be pre-calculated as soon as you've created the virtual world. The other methods have to be done for each frame whenever you're updating the screen, but this method can be done because it's applicable for all viewing positions in your virtual world. Right. Okay. By the way, I said Painter's algorithm is quite obvious what it does. Backface culling as well, culls any backfacing polygons. Same thing with binary space partition. Anybody know what binary means?
1 and 0.
What? Sorry?
1 and 0s.
Yeah, one and zero, one or the other. You've got two states. So binary means you've got two states. Space is obvious, we have a space. What does partitioning mean? Splitting up. Yeah. So binary space partition basically means splitting up your space into two. Okay, so bear that in mind. Now, before we continue with binary space partitioning, there are a few terms which we need to have a look at. Okay, convex set. When I refer to a convex set of polygons, this is a set where each polygon is facing every other polygon. So you know, basically think of these as people. Okay, so these two polygons are both facing each other, they're having a chat. They form a convex set. These two polygons don't like each other. They've got their back to each other. So that's a non-convex. If this polygon here was facing this one, but this one's still facing away, it still wouldn't be a convex set. They've both got to be facing each other. So that's what we mean by a convex set. Your polygons, your normal vectors, are facing towards each other. And there is a rather great, I like this term, I don't know why, it just sounds all sort of sci-fi and stuff. An atomic subspace is a space that contains a convex set, which means all polygons within this subspace are all facing each other. Okay, hyperplane. Gets really sci-fi now. A hyperplane in n-dimensional space is an n-1 dimensional object that bisects a space into two. So if you had a 3D space like this, we insert a 2D hyperplane and it will split it into two subspaces. Binary tree. We mentioned that binary is one or the other. Okay. Have you seen graphs before? Mathematical graphs. Basically, a tree is a mathematical graph. Okay. A binary tree consists of nodes and branches. So here we have got all these nodes. I've labelled them A through to G. And with a binary tree, each node has at most 2 branches stemming from it. But never have more than 2, because then it wouldn't be a binary tree. Nodes that attach to branches of a node are called child nodes. For example, A has 2 branches coming off it, and B is one of the nodes. B is a child of A. And A is a parent of B. A node without a parent node, so for example, A doesn't have a parent node, that's called the root node. And a node without a child node is called a leaf node. Okay, so if I was to turn this upside down, it will sort of resemble a tree. But the convention is that we do them, well, in binary space partitioning, we do them facing down. But like a family tree. But a family tree, each node can have at most 2 children. You can have 2 children, 1 child, or no child at all. And this is what we do. This is in sort of formal algorithmic sort of, explanation. So we have a function, S. So our input to our function S, and S is the set of polygons. If S is a convex set, then we don't have to do anything. We can quit. Okay. Remember what I meant by a convex set? All polygons are facing each other. However, what we do is we choose a polygon in S, and at this stage it doesn't matter which one, but we'll see in a minute why. And we insert a hyperplane along that polygon. So what we're going to do is you've got lots of polygons in a space, you choose one of those polygons, and you insert a hyperplane, so it cuts all of the space into 2. For all other polygons, if it's in front, if you're in the front subspace, you add that polygon to the left child node. L, I'll call it L for left. If your polygon, however, is behind H, then you add that polygon to the right child node. And then what you do is you repeat the function for each of those subspaces. So when you insert a hyperplane in, you're dividing the space into 2. All of the ones in the front subspace, you repeat. And you also do the same in the back subspace. Eventually, every time you call this function, you're going to get to this point where you have a convex set. So eventually, what you have is all of your nodes are a convex set. That may sound really weird. It's a lot easier than it sounds. Okay. Start off with a very simple example. Here I have a space. I have 3 polygons in that space. I've chosen polygon A to be the root node, so I insert a hyperplane along polygon A. So this cuts this space into 2. So I've got the front space, the one in which the normal vector is pointing towards, and I've got the back space. In the front space, B exists, so I stick B in the left child node, and in the back space, C is contained in the back space, the C is listed in the right child node. That's all it is. If you've got coincident nodes, or coincident polygons, what I mean by coincidence is 2 polygons which exist on the same plane and have normal vectors pointing in the same direction. So for example, A and B are on the same plane and have normal vectors pointing in the same direction. I can group those. Okay, so I can include them in the same group node there. So in this case, C is in the front space and D is in the back space. And coincident polygons can be treated as one, which is quite handy. Okay, so I'm going to go through a worked example. Here I've got 4 polygons. Okay, I've chosen C to be my first polygon. I'm going to slap a hyperplane along C. So I've now got 2 spaces. In the front space, I've only got polygon D. So D exists on its own in the front space. In the back space, I've got two polygons, A and B. Now you might notice something sort of slightly subtle here. I've used a circle for D, but a square for A and B. The reason being, and you don't have to do this, it's only something I do, D is a convex set because there's no other polygon for it to be facing away from, so therefore it's a convex set. A and B are facing away from each other, so they're not a convex set. So I represent the node with a square just to show that that's not convex. By the way, you don't have to do this. I find it helps when I'm actually working these things out. Okay, so I've got this so far. Now I need to continue until all of my nodes contain a convex set. Now, because A and B is not convex, I need to split this space up. So what I'm going to do is I'm going to insert a hyperplane along B. And the hyperplane extends from the edge of the space, which is to that point there, because we're only dealing with this space, okay, and it goes through A. So it cuts A into two. So instead of one polygon A, I've now got two. I've got A1 and A2. And A1 is in front of B, so that goes in the left child node. A2 is behind, it goes in the right child node. And that's basically the BSP tree for that simplified example. Okay, you might notice something strange here. Why did I choose B to actually insert the hyperplane along? If I'd chosen A, the hyperplane would have done that and not cut B at all. And then I wouldn't have this additional polygon which I had to split. Well, the reason I did that is I wanted to show you the example of splitting. But it can also be considered when we have an optimal binary space partitioning tree. Okay, there are two criteria in which we can optimize. One is the number of polygons. More polygons in a virtual world means more work. So we want to cut down on that. So when a polygon is split, the number of polygons increases. If we have a poor choice of where we put our hyperplanes, we have a growth factor up to 2 to the power n, where n is the number of polygons. So that's the first criteria. We want to minimize the number of times we split polygons. Second one is having a balanced tree. Now, a balanced tree is where we have a similar number of nodes to the left and to the right. Now, the good thing about a balanced tree is it's more efficient to traverse, which we'll see what we mean by traversal probably in the next lecture. And we have fewer levels to deal with. So there's my example. Okay, so that's for the second hyperplane, I put it along B, which split A and B. Sorry, A1 and A2 apart. Whereas if I just put it down A, you can see I've got fewer polygons. How do you minimize splitting? No easy way of doing it, really. To minimize it, we check a sample of polygons to see how many splittings will occur and choose the one that results in the minimum number of splittings. We can't check them all, right? If we had 20 polygons, which is really small for a virtual world, I think the one I showed you earlier had something like 40. I mean, the one with the houses and the church and things like that. So if we had 20 polygons, we wanted to check them all, that would be 20 factorial number of checks, which is 2.43 times 10 to the 18. So that's 243 followed by 16 zeros. Put that into perspective, at 1 microsecond per check, it would take you 77,000 years to actually generate your BSP tree. Obviously, we can't do that. So in practice, we take a random sample of around about 5 polygons and check whether they minimize the splitting. Okay. Why do we take about 5? somebody's done a study into this. And what this graph represents is, along the bottom we have, this is the sample size of each polygon. So for example here, we only sampled one polygon per sort of hyperplane. Here we had a look at two. We chose the one with the fewest splittings. Here we had a look at three randomly. So this is totally random. Do it several thousand times, and you get this type of graph. So when you only pick one polygon, the number of splittings increases by about 190%. If you pick the best of two, it goes down to 140% increase. Best of three, about 118%. And as you go down here, you can choose 20 polygons. You're not actually getting a significant saving over choosing around about 5. So in practice, we take about 5. Almost finished. I mentioned earlier about balanced and unbalanced tree. Essentially, we mean we've got more. We've got about the same amount of nodes on both sides. So here's a root node, and it's got 3 nodes on each side. That's a balanced tree. Here's an unbalanced tree, which obviously got more nodes on one side than the other. But the problem is, if we seek to minimize the splittings, we're going to end up with an unbalanced tree. Now, if we seek to try and get our tree as balanced as possible, we're going to increase the number of splittings. So there's a trade-off here. Okay, so there's a trade-off between minimizing splittings and balancing the tree. In practice, to do this for real, you create several trees and just choose the one with the best combination. You're never going to get it exact. It'll take 77,000 years to do that. Right, I'm going to finish this one here. You may be very confused with this BSP tree malarkey. I promise you it's dead easy. Okay, and it is part of your assignment. So, if I can find the assignments. We have a look at assignment 7. Question 2. I say blah 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 blah. Apply binary space partitioning to the virtual world and express the result in a binary tree. Okay. In our next session, which is in an hour's time, we'll be looking at the activity which is very, very similar to this. And every year, this is like the favourite sort of question that students like, because it's actually really clever. Not my questions are clever. I mean the BSP process is really clever. Okay, right. I guess you're all a bit confused. Bear with me. Have an hour break, and then I'll reveal all in an hour. Sorry. Number theory. What? How to count? Okay. By the way, if you like number theory, go and watch the film Manu Infinity. You heard of it? It's all about Hardy. Have you heard of Hardy? The manager? No. G.H. Hardy, very famous number theorist.
I've been to on YouTube looking at these things, so I'm forcing something at some point.
Yeah. When's the number theory in?
Next week.
When's the numerical methods in? It's already been in, has it? Some people were working on that in the last lecture.
So yeah, I won't be in the lecture again.
Right.
Going on later today.
What I'll try and do then is, because it's this last one here, it's kind of going to kind of help you with the assignment. So anything I write down, I'll scan it.
Yeah. Right. Thanks, guys. Cheers.
Yeah. 3 times 4. 5 times 6. out.
answer.
So I joined his hopes and dreams.
I thought I'd done it. I thought we'd cracked the most difficult question
In the
in
universe.
not about the universe. But
RSA encryption.